So let us see the different types of the overlapping of orbitals. Suppose we have two s orbitals. S orbitals. As you know, s orbitals are spherical in shape. See, here there is an atom with a s orbital. This is the nucleus of the combining atom, s orbital. Then there is the second atom, and that is also having s orbital. Suppose both the atoms are having s orbitals. When these two atoms approach each other, the two orbitals will be merging together. The two orbitals will be overlapping. See, in this there is one electron. In the, say this one, there is one electron. Here also there is one electron, suppose. So half-filled, singly occupied s orbitals are going to merge. And during merging, what happens? Say this is the situation. Here there is the nucleus of the two atoms, nucleus. Say the nucleus of the two atoms. And here we have the electron pairs between them. So there is merging of the s orbitals. This is s orbital, another s orbital, and they are merging together. During this process, what happens? There is electron pair. There is pairing of electrons. That means a pair of electrons will be coming between the nuclei. And there is a common space for a merging, and that is the overlapping. During this process, the overlapping takes place in a coaxial manner. There is a coaxial overlap of the orbitals. Coaxial overlap. That is also known as end-to-end overlap. End-to-end overlap, or head-on overlap. Head-on overlap. Coaxial overlap or head-on overlap or end-to-end overlap. What is meant by coaxial overlapping? You consider an axis, a line, an axis passing through the center of the orbital. Suppose here, say this is the axis of the s orbital 1, s orbital of atom number 1. And here, the axis of the second atom. And the two s orbitals are going to overlap in such a way that there is a common axis for both the overlapping orbitals. And that is called coaxial overlapping. That means overlapping along the same axis. Axis is nothing but an imaginary line passing through the center of the orbital. An imaginary line passing through the center of the orbital. That is called the axis of the orbital. Say here, the two s orbitals, they are having their own axis. And during merging or overlapping, the axis will be common for both the combining atoms, both the overlapping orbitals, and that is called the coaxial overlapping. So the covalent bond formed by the coaxial overlapping of atomic orbitals, that is known as sigma covalent bond. The symbol is this, sigma, that is sigma covalent bond. So what is sigma bond? What is sigma covalent bond? Sigma covalent bond is the covalent bond formed by coaxial overlapping or end-to-end overlapping or head-on overlapping of two atomic orbitals. Here we have the s-s overlapping. When two s orbitals overlap, there is always coaxial overlapping. And the bond formed by coaxial overlapping or end-to-end overlapping or a head-on overlapping of the orbitals, that is called a sigma bond. So that is one type of covalent bond formed. Let us take the case of say two p orbitals. Here there is one p orbital, and this is the position of the nucleus. P orbital, that is a dumbbell in shape, and this is the axis of the p orbital. Another atom, say here there is another atom, and that is also having say p orbital, and this is the axis of the second p orbital. Now these two p orbitals are coming face to face, and they are going to overlap along the same axis, coaxial overlap. And the coaxial overlap will be, say, like this. We can show it, say, like this. Here there is one p orbital, and here there is another p orbital, see? This is one p orbital, and this is another p orbital, and here there is overlapping, and the axis is common. The axis is common, that is common for both the p orbitals, a common axis, say coaxial overlapping, and here there will be, say, common space or an overlapping space between the p orbitals, and this is pp overlapping, and this is also coaxial, and so this is also a sigma bond, sigma covalent bond. That is again the coaxial overlapping of two p orbitals. Okay, let us see the case of the overlapping between s orbital. Here there is a s orbital, and here there is a p orbital, suppose. And see, there is an orbital in this way, and here during this overlapping there is a common axis for both the orbitals. There is s orbital, here there is p orbital, and there is a common space, say, between these two. There is a common region between these two. See here like this, and here there is coaxial overlapping again, and that is also a sigma covalent bond, So in general, sigma covalent bond is the covalent bond formed by coaxial or head-on or end-to-end overlap of two orbitals. For example, coaxial overlapping of two s orbitals, coaxial overlapping of two p orbitals, coaxial overlapping of one s orbital and one p orbital. Come on, Navin.
I'm not getting the coaxial thing. Like how is it that infinity?
Axis is the common axis of say, you look here. Here there is the s orbital, and this is the nucleus. Suppose a line passing through the center. That's a sphere. At the center of the sphere there is the nucleus. That you know. Now suppose an imaginary line. An imaginary line passing through the center. That is called the axis of the orbital. Okay. Similarly, you take the p orbital. Here there is the nucleus, and there is the dumbbell. Say dumbbell. The two lobes. This is called a lobe. This is also lobe. Two lobes. The two lobes are identical. Just like a balloon which is blown and twisted at the center. Okay? A balloon is blown, inflated, and that is twisted at the center. This is the center. And that consists of a p orbital, the shape of a p orbital, the balloon model of the p orbital. Do you get it? And in the p orbital, there are two lobes, two parts, two halves, two halves. And each half is called a lobe. Lobe. So the two lobes are symmetrical in the case of a p orbital. And this is the axis of the p orbital, because the axis should pass through the center of the orbital. That is center of the two lobes. Center of the two lobes. See? So this is the axis. Now these two are going to merge, overlap. Then what happens? The two orbitals are coming along the same axis, same direction. And there is, see this one, there is a common axis for both the orbitals. And it is called the coaxial overlapping. Agreed? Do you get it?
Yeah, I got it.
So any type of bond formed by the coaxial axis is an imaginary line. There is no such thing. It is an imaginary line passing through the center of the orbital. That's all. Okay. So here there is the overlapping as in such a way that the axis of the two orbitals are in the same direction. Axis of the two orbitals are in the same direction. And there is overlapping. And it is called the coaxial overlapping. That is also sigma bond. So the sigma bond may be formed by S overlapping. Two s orbitals, coaxial. Or it may be coaxial overlapping of two p orbitals. Or it may be coaxial overlapping of s and p orbitals. As it is shown now.
The s orbital is the circle and the other one is the...
Not the circle. That is not the circle. You are taking the... Okay, tomorrow I shall bring the balloon and I'll show that. Okay, it is not the circle. It is having the appearance of this. A balloon is blown and it is twisted. And if you observe, say from a distance, you will be getting the shape of a loop twisted. You will be getting the shape of 8. It is not 8. Similarly, this one, it is not a circle. It is a sphere. You take the cross section of a sphere, cross section.
Okay, got it. I got it.
You take an apple, an orange, and you just divide it through the center. Then what will be the shape of the point of a section? The cross section will be having the circular shape. It is not circle. This is only, we can show it only this way. Because here is a three-dimensional. There is supposition. There is supposition. Suppose this is the sphere, not a circle. This is not having the shape of 8. No. This is not circle. It is spherical. It is spherical. I shall show it bringing the balloon models the next day. Okay. So this is not a 8. This is not a circle. Here there is a balloon. Spherical balloon. One side balloon. Okay. Balloon. And the other side same. The s orbital is not a circle. Don't be confused. It is not a circle. It is spherical. Yeah. Suppose you have a ball. A rubber ball is there with you. And that is having the shape of a s orbital. Okay. A ball, rubber ball. Now you cut it through the center. You will get two hemispheres, no? Two hemispheres. And look at the cutting point. That is the cross section. It will appear like a circle. That's all. It is not circular. It is not circular. Okay. Now the merging is this. We have a ball here. Balloon. Inflated balloon is here. There is another inflated balloon. At the center there is the nucleus. Okay. Two spheres are coming closer. And they are coming and see, merging together. I shall bring it the next day. Okay, if there is a confusion, we have to make it clear. Okay, I shall do that. Similarly, during PP overlapping, the balloon is blown and is twisted at the center, then you will get the shape. The shape is called a dumbbell. Dumbbell. It is not the shape of 8. It is not the shape of 8. It is dumbbell in shape. Okay. So two dumbbells, two balloons, two dumbbells are coming and they are merging together along the same axis. Then it is called a coaxial overlapping of a two p orbital sigma bond again. Then a circle, a sphere, and there is the p orbital, that is dumbbell, and these two are coming closer along the same direction, same axis, and there is sp overlapping. Okay, that is called a sigma orbital, sigma covalent bond. Okay, now tetrahedron will be having this shape, the shape of the tetrahedron, and it's a regular tetrahedron. Regular tetrahedron. And what is meant by regular? All the edges are equal. Now, we have the triangles. You take the front triangle, say facing to you. Say the three sides of the triangle, all these are equal, equilateral triangle. Similarly, this side, equilateral triangle, this side, equilateral triangle. Can you see this?
Yes, sir.
Okay.
Yes, sir.
And at the bottom, there is a equilateral triangle. Okay. So, if all the sides are equilateral triangles, or if all the edges are equal, then it is called a regular tetrahedron. Tetrahedron. So, it is having this shape. And the atom, the Achyut, Anthony, Steffi, Adim, can you see the model? There should be an idea about the model in your memory. Otherwise, you cannot get any idea of this. Okay. So at the center of the tetrahedron, see here, at the center of the tetrahedron, there is the atom which is undergoing hybridization. At the center, see, at the center, inside this one, inside the very center of this figure, there is the atom which is undergoing hybridization. For example, carbon atom, it is here. Then we have 4 sp3 hybrid orbitals. 4 sp3 hybrid orbitals. And these are directed towards the corners of the regular tetrahedron. At the center, see here, at the center here, at the center there is the atom which is undergoing hybridization. At the center, okay? Can you see this?
Yes, sir.
Yes, sir.
At the center there is the atom undergoing hybridization. And from that atom, we have 4 sp3 hybrid orbitals, and these are directed towards the corners of the tetrahedron. One is going upwards, one is going to this corner, other is going to that corner, and the other one is going to this corner. See? That will be the direction. So what happens? You will be getting a figure like this. You will be getting a figure like this. Do you follow? Can you see this?
Yes, sir.
You will getting a figure like this. Okay? This one. So here there is the atom which is undergoing sp3 hybridization. sp3 hybridization. Rajas, Anthony, after sp3, we get 4 sp3 hybrids. 4 sp3 hybrids. And these 4 sp3 hybrid orbitals are directed towards the corners of a tetrahedron. At the center, there is the atom, this one. And the sp3 orbitals are directed towards the corners of the tetrahedron. So, 1 sp3, second sp3, third sp3, fourth sp3, okay? Fourth sp3, this is not A planar molecule. This is a three-dimensional figure. Three-dimensional figure. Your class now. 1 minute. So three-dimensional figure. So this arrangement is called tetrahedral arrangement. This is called a tetrahedral arrangement. Now the other atoms, the other combining atoms will be coming in this direction, in this direction, in this direction, and in this direction. Okay? Followed? Then you get a molecule. See, a molecule like this. 1 minute more, 1 minute. Otherwise, I have to repeat the whole thing the next day. So it will be having the shape like this. So the shape of the molecule, let us see. Press it. Okay. Here also. Okay. So the shape of the resultant molecule will be like this. The shape of the resultant molecule is like this. Do you get the idea?
Yes, sir.
Yes, sir.
Do you
Yes,
get me?
sir.
Yes.
Eh?
Yes, sir.
This picture should be there in your mind when you speak about the tetrahedron. It is not a planar molecule. It's a three-dimensional figure like this. This is the atom undergoing hybridization, this one. The central atom that is undergoing sp3 hybridization. Okay? And one sp3, second sp3, third sp3, and the fourth. Say 1, 2, 3, 4 sp3. And the sp3 will be overlapping with the orbitals of the other atoms. And the resultant molecule will be having this shape. Okay? And this shape is called tetrahedral shape. Tetrahedral shape. So wherever there is Krishna, wherever there is sp3 hybridization, the geometry is tetrahedral. The shape is a tetrahedral. The geometry is a tetrahedral. Okay? And the bond angle. This is the bond angle. The bond angle. You measure this bond angle. That is 109 degrees, 28 minutes. 109 degrees, 28 minutes. All the angles will be 109 degrees, 28 minutes. And it is called the tetrahedral angle. Angle within the tetrahedron. It's called the tetrahedral angle. So it is more time. Let me stop now, my dear friends. Others are waiting.